So, so this is the title. I will be giving a glimpse of what we have been doing for the last 3 years. Everybody's familiar with the successes of machine learning, so plenty of them, lots of them, from self-driving cars, image and speech recognition, personal digital assistants, and so on, okay? What is explainable AI? So the idea is that we have this AI system which is very complex, and we would like to help humans to understand a machine learning model that is opaque or black box, okay? And there are lots of questions we can ask. So essentially, we are interested in answering why questions, why the prediction, why not questions, why not some other prediction. And in our case, we are interested in what are the guarantees of rigor that we have. And there are other queries that are related with these problems, like listing in explanations, deciding whether a feature is important for an explanation, and so on, okay? And so you could ask, is this important? Well, of course, we have ANITI. This is just a glimpse of regulations that are, at least in Europe, that exist, that essentially imply that we should have XAI. GDPR, guidelines for ethical uses of trustworthy AI, a recent regulation, and some people arguing that GDPR entitles you to the right of an explanation. And of course, there are efforts in the US. Okay, so this one of the regulations I just mentioned, it's a proposal and essentially characterizes uses of systems in terms of risk that they can have. You can have systems with an acceptable risk, and here you cannot use AI. You have systems of minimal and limited risk, so here we are not worried about the uses of AI. And then you have systems of high risk where we are very worried about the uses of AI. Concrete examples include law enforcement, creditworthiness, management, operation of critical infrastructure, and so on, okay? And then you have safety critical applications like self-driving cars and autonomous vehicles, where, well, if you have an accident, you should at least be able to explain what went wrong, okay? And so for that reason, some authors have argued that we should stop explaining black box machine learning models for high-stakes decisions and use interpretable models instead. Okay, so this claim is important. This lady received this year a very important award because of this work. And so in this setting, the correctness of explanations is paramount. Okay, so okay, so this is important to build trust, help debug AI systems, and prevent accidents. Okay, so this is the motivation for our work, and so this is the outline. So I'm going to talk a little bit about the limitations of what exists. What we are defining what we mean by formal explainability, and summarize the progress that we have made, and talk a little bit beyond just computing explanations. Okay, so that we are all on the same page. We have a set of features, just numbers, and each feature takes values from some domain: Boolean, integer, real, categorical. It doesn't matter. Okay, and this allows us to define a feature space. And besides features, we have classes, and a machine learning model for us computes a non-constant classification function that maps feature space to classes. Okay? And concretely, we are interested in points in feature space. We call it an instance where we have a point and the associated class. So this is what we are trying to explain. So what most people talk about, some people even in ANITI, is essentially model-agnostic explainers. So there are different ways of doing this. The most famous are Lyman and Sharp, for example. They learn a very simple interpretable machine learning model. So for example, linear classifier, but they could also learn a decision tree. And the idea is that you train a classifier, different ways for doing that, and then this is your explanation. A different approach is anchors. So you learn the features that you decide that they are important for the prediction. And like a LIME, it is sample-based. Now, an important point to make is that they offer no formal guarantees of rigor in the explanations they compute. Okay? So this is one way. Another way proposed, I mentioned one of the papers in a few slides back, is intrinsic interpretability. So the idea is that the model itself, it is interpretable, and that is the explanation. Okay? So one example are decision trees, decision lists, decision sets, and so on. So the first question we asked in 2019 was, can we really trust these things? Okay? Can we trust model agnostic explainers? Is intrinsic interpretability indeed interpretable? So back in 2019, we looked at the boosted tree for a very well-known data set. So this is a very simple boosted tree to fit on the slide. We have 7 classes, and for each class, we test just one feature, predict the number, and then we pick the class with the highest number. Okay? And so this is an example of an instance. So if all of these feature values are true, then the class should be reptile. Okay? And what we discover, so essentially we ran anchor on this, and the anchor says, okay, so if you don't have not air, not milk, not tooth, not fins, class is reptile. Okay, so for us, this is the explanation. So if you don't have hair, you don't have milk, you don't have a tooth, and you don't have fins, you predict reptile. Yes? This is what anchor says. And then we discovered, even in training data, that for a different instance, well, where the explanation is true, the class is different. It should be amphibian. Okay? So usually people don't really say, okay, so it's reptile or amphibian, why should I care? So let me translate this to something we care more about. So suppose you have a classifier for deciding bank loans, and you have 2 samples, Bessie and Clive. The bank loan for Bessie was approved. The bank loan for Clive was not approved. Then you come up with an explanation, say age 45, salary 50K. And then what you discover is that X is consistent both with Bessie and with Clive. So the idea is that you have different outcomes and you have the same explanation. So if you don't see this as very problematic, let me give you a different take. Suppose you have a classifier for a serious medical condition, okay? And you have 2 samples, a guy that is ill, Ilan, and a girl that is healthy, Ether. And you have some explanation. Again, I'm not a medical doctor, so it's attribute 1, not attribute 2, and attribute 3. And then this explanation is consistent with both the guy that is unwell and the girl that is very well. Okay? So again, different outcomes and some explanation. So a medical doctor would be thrilled to have this explanation. Okay? So you could say, well, that doesn't happen, and actually it happens a lot. So these are different data sets, and these are the explainers that I mentioned. These are incorrect explanations, redundant, meaning you can drop features, and correct. And for some data sets, most of the explanations we could find were incorrect. So they are consistent with other predictions than the prediction we are interested in. And so when I say most of them, it's 99.7, 99.4, and so on. It's a pretty big number. Okay? Very good. So this was the first question. The second question was interpretability. So should we just use interpretable models? And so actually, if I was to ask everyone, if I would ask you, are decision trees interpretable? I would say 99.9% would say yes. So the general agreement, actually, there is even a paper from 21 years ago saying on interpretability, trees rate an A star. Okay, you cannot get better than this. And actually, one of the papers I mentioned at the beginning of the talk was proposing exactly this. Just use decision trees, okay? So let's look at decision trees. And so what we did was we went to this paper. Everybody knows NeurIPS, okay? And actually, the paper has a great name, Optimal Sparse Decision Tree. So this is the tool. And the tool, this is taken from the paper. So we went to the paper, got the decision tree. So this is the decision tree from this paper using that tool, yes? And so we looked at this path here. And so ask the question. So what is the explanation when MM is this, right? 0, TL is 0, BR is 1, BL is 0, TR is 1. Well, because the model is interpretable, it's the path, right? So that's the explanation. Okay. And so we said, okay, let's now understand this better. And so this is the explanation we would propose to, let's say, a medical doctor. And we decided to do a little bit more. So this is the path. And we looked at the combinations of values for MM, BL, and TL. And for all possible combinations, the prediction does not change. So the bottom line is that we can have an explanation which is just this guy and this guy here. Now, I hope you agree with me that the medical doctor would be much happier with this explanation than with this explanation. Okay. So this is the point is that actually proves that decision trees can be arbitrarily redundant on the number of features. So if you have m features, you can have m-1 redundant features on an explanation. So, well, so essentially this tool is great for us. It was great because first, well, it's optimal sparse decision trees, but we show there is redundancy. And actually, the percentage of paths with redundancy is, redundancy of explanations is pretty significant, okay? Very, very well. So it's also priceless because in the same paper, they propose another decision tree. And this is fantastic because although the title of the paper is optimal sparse decision trees, this tree is everything but optimal. Why? Because, well, here you test add square, add equals square. So no matter what you do here you are going to repeat a test. Well, this is yes or no. So I mean, you don't need it. You can just put yes or no here. You don't need a test. So it's not optimal. So this suggests that a lot of software that is being used in machine learning is buggy, or at least the claims of optimality should not be there anyway. Okay, can I continue? Yes. So, but again, you could say, well, nobody cares about that. Let's look at serious problems. Like this is a tool used in precision medicine, MediBoost. So this is the decision tree generated by this tool. It looks fantastic. Well, we discovered that is full of unnecessary tests. So this test is unnecessary, this one, all of this is unnecessary, all of this is unnecessary. So essentially, well, at least they don't claim it's optimal, but all of this is completely relevant. You don't need it there. So this means you are essentially confusing the medical doctor that is looking at the decision tree, number one. Number two, well, suppose the prediction is here -1. So it's easy to prove that you don't need this test, you don't need this test, you don't need this test to predict -1. Why? Because if you flip it, you get -1 anyway. Okay, so we can give explanations that are much more succinct than what the tree is giving. So you could say that, well, you guys spent 3 years looking for examples in papers. That doesn't happen in general. Okay, so we went back to the books. This is, well, I presume everybody knows this book, Russell and Norvik's AI book. And so look at this decision tree. This is what they propose. And suppose that you have full, yes, tie, no. So the idea is that here you can drop this test, so you really don't need to know hungry, if you are hungry or not. You are going to predict no anyway. So you have redundancy in your path in terms of explanations. Okay, so if this example looks too simple, we went to another well-known book, Pullman, of course, book, and here it's full of examples. So if the prediction is skips, you don't need this test. If the prediction is reads, you don't need this test and so on. Okay, so lots of redundancy in explanations. So you could say, well, you're lucky, 2 books. What we did is we went through most of the books in AI and machine learning. So we went back to, I think, 84. So this is the Bremen book on CART. And this is, we just highlight here the percentage of paths that are redundant in those examples. And this is the average number of literals that are redundant. As you can see, the percentage of paths that can be redundant can be quite significant in some cases. And these are small examples used in books and papers over the years. Okay? So, and of course, the percentage of literals that are redundant can also be quite significant, as I show here. Okay, so let me introduce now formal explainability, and this is what we have been doing. Okay? So we start from an instance, and an abductive explanation answers a why question. So we want to know why the prediction, and we want to find a subset minimal set of features that is sufficient for ensuring the prediction. How do we represent this in logic? Well, we say we look at all points in feature space, and if we fix the guys that are in X, then we guarantee that the prediction is what we want. Okay? And you could say, okay, but how can you look at all points in feature space? Well, we have reasons for that. Okay? There are automated reasoners that do this. Okay? Now, a contrastive explanation answers a different question, the why not question. And so it's a subset minimal set of features that is sufficient for changing the prediction. So the idea is that I'm able to find a point in feature space. If I fix all the other features that are not in the set, the features in the set are enough to change the prediction. And how do we get subset minimal? Essentially, we need this predicate to hold true, and then for any subset, it must not hold true. That is pretty standard. And so we can define abductive and contrastive, well, by saying it has to be weak, and for any subset, it's not weak. It has to be weak, and for any subset, it's not weak. Okay? And so what we also proved is that abductive, with Nicholas, is that abductive explanations are minimal heating sets of contrastive and vice versa. So this is very important to navigate the space of explanations. What we proved a few more things. So we can simplify that condition over there because there is monotonicity with respect to set inclusion. And so the definition of abductive can be simplified. We don't need to test all subsets, but just a few sets, just dropping one element at a time. And so this allows us to have a very simple approach. We just navigate through all the features one at a time, define abstract predicates, one for abductive, one for contrastive explanations, and then we can have a very simple algorithm that will give us a subset minimal abductive or contrastive explanation. So this is what we have been doing for different classifiers. Now, of course, the question now is, sure, this is great. How do you do it for neural networks, for random forests, boosted trees, and so on? And this is where we have spent the time, how to find these encodings. Okay? So let me give you just an example. So this is a very simple neural network, just to show that what we are doing does not have serious conceptual limitations. As far as we know, it doesn't have any serious conceptual limitation. So each layer is viewed as a block, and what we do in each block is we compute an intermediate value x prime given the input x and the weight matrix and some bias vector. And then we compute the output given the intermediate value x prime, given some activation function, and we use ReLU for that. Okay? How do we do this? Well, so what I said in the previous slide is summarized here. So we compute an intermediate value, and then we take the max, which is ReLU. How do we do this now? Well, we can do is, well, the dot product here, it's a bunch of weighted summations. And because the summations can be positive and negative, what we do is that we do the difference between two non-negative variables, and then we use a Boolean variable to decide which one is going to be non-zero. Okay? And so why is this important? Because if the summation is positive, we put it in the output, and if it's negative, we put it in some slack variable that disappears. Okay? That's the idea. So just to give you an idea that this is what we do. So we start from from a neural network, and then this is the mixed integer linear programming encoding. And this shows how we can use it by hand. Of course, in general, we just use an automated reasoning for this. Okay? Very good. So some results that we got at 2019. So this is with a subset minimal, smallest explanation, which I did not really explain. And the time we spent on average for computing, on average, the minimum and the maximum time. And as you can see, well, sometimes we can spend some significant amount of time, and sometimes we cannot finish when we want the smallest possible explanation. So what is the take-home message from this table is that first rigorous approach for explaining neural networks in 2019, 3 years ago. That's the good news. The bad news is that it scaled at a time to a few tens of neurons, and it still scales for a few tens of neurons. So you could say, okay, so why bother? Well, we have been much more successful with other classes of classifiers, and that's what I'm going to talk about. So just very quickly, we show that for some classifiers you can do it even in polynomial time to compute explanations. Let me explain how you do this here. So the idea is as follows. We could just run a PI explanation algorithm, as I explained a few slides back, using NP oracles. This would be worst case exponential time. But here it's really not important. Suppose we have prediction 1. And so what we want to make sure is that as we say that features are not important, we want to make sure that we don't allow a path to 0 to become consistent, okay? And so we want to ensure that the paths with prediction 0 remain consistent. So essentially I want to drop features, but I want to make sure that this path and this path and this path are hit by literals that are inconsistent. And so this is, essentially we need to find the minimal, not minimum, minimal hitting set, and this we can solve in polynomial time, okay? So essentially here, we know we can prove that if this guy is fixed and this guy is fixed, and so here it's also fixed, the prediction is going to be 1 no matter what. And this is what I mentioned at the beginning of the talk. Okay, so some results for decision trees. Again, I'm not going to spend a lot of time, just to say that this tool has been around for 2 decades. This tool is a commercial product from the US. for the last 2 years, 3 years. And what we notice is that it really doesn't matter. The percentage of pads that are redundant can be quite significant. Okay? So when people say that they are giving you interpretable decision trees, it's really not true, because they are giving you trees that will for sure have a huge number of pads that are explanation redundant, and you can drop those literals. And the percentage of literals in redundant pads can also be quite significant in both cases. Okay, so first take-home message. Let me just summarize the progress that we have been making. So, of course, we looked at naive Bayes classifiers, decision trees, decision graphs, decision diagrams, and monotonic classifiers, propositional languages, and so on. All of this we can prove in polynomial time, so they are in this. So here, this plot summarizes whether we are effective or ineffective in practice to compute an explanation. And here is the computational complexity. So these guys here are the green boxes here. We can compute one explanation in polynomial time, and they are terribly efficient. Okay? It's a fraction of a second. This is easy. For some others, we prove that they are computationally hard in theory, but in practice, they are very effective to compute. So that is the case with decision lists, random forests, and boosted trees. So they are DP complete. At least we proved for this one it is DP complete, but it doesn't matter because in practice it takes a few seconds to compute. Okay, and of course we still have some walls to cross. Bayesian networks and neural networks, they are computationally hard, and we still don't have a way to compute them efficiently. Okay, so just you could say, well, can you convince us of the results? So let me try to convince you. This is for random forests. Again, we have different ways to do it. This is one way to do it with SAT, a SAT oracle. And this is the average runtime. It's shown here. And this is the percentage of wins with respect to anchor. So at the beginning of the talk, I introduced anchor. I said anchor is very problematic. Well, we decided to compare against anchor anyway in terms of performance. And what we concluded is that it's our approach, which is solving a computationally hard problem, is way faster than anchor on average. Okay, so it doesn't really matter that we are solving a hard problem. We solve it very efficiently. So that's what the bottom line. Okay, so let me continue. What we have done besides this? Well, we have looked at enumeration. We have a bunch of papers on how to enumerate explanations, both abductive and contrastive explanations. We have looked at the membership problem. So suppose you want to know if a bank loan application is using age to decline a bank loan. Okay, so this is the membership problem. We want to know if when we decline a bank loan, for example, was age used for declining the loan. Okay, and so we proved some complexity results, and we have some implementations for this. Another line of work has been probabilistic explanations. Why? Because if the explanations are too large, people cannot understand them. So what we are trying to do is find smaller explanations which are not as rigorous, but that are still rigorous enough, so we can guarantee with some probability that the prediction is what we are explaining. Okay, and so on. So yes, so the idea here, the goal is to reduce explanation size compared to completely rigorous explanations. So this is, I have 2 more slides before. Critical limitation. I talked about the critical limitations of XAI approaches. I introduced formal explainability. So this is what we have been doing for the last 3 years. And then I talked about a bunch of problems that we are looking at. So you could say, what have you done with this? So this summarizes the output. And again, we cannot see that, but it's a small sample of deep level publications. So what I'm showing here are just papers on, most of the papers on explainable AI. So, well, we usually use Core for that. So Core A star is pretty good. Core A is okay. Core B is not so good. Others, it depends, it might not just be ranked. And a number of the year and the totals, okay? And so that's it.